All right, hey, so I'm just kind of catching up on some loose ends here with 242. So we're going over that Hellgate wind turbine project again. So let me walk you through that. The question asks if we're given a wind speed. So here's the Hellgate turbine sitting here. This is ground level right here. I said the wind is blowing at 40 miles per hour, 40 mph, right through the turbine. The turbine is spinning. And I've told you that there's 10 kilowatts of electricity coming out through the copper wire underground. I've given you the air density, rho of 1.2041 kilograms per cubic meter. The efficiency, ooh, that's weird. I've overpowered the journal. Oof.
I'm not confused.
That's a new one. Wow. Okay. I said we're just assume, this is kind of an upper limit assumption that we're operating at the BETS efficiency, which is 16/27. So what I've asked you to do is tell me what the swept area of the turbine equals. So we're given the velocity, we're given the power out. Weird. Wow, that's a new one. Just as I was about to make some fantastic progress there. Hold the phone, it's a conspiracy. Forgot to record that, so bear with me. I'm just going to go through it one more time. Yeah, so we'll go through it one more time.
Me, because the first time I'm just trying to.
Yeah. Cool. All right, so we'll take it from the top here. We've got a good solution going. So again, the velocity of the wind through this spinning wind turbine is at 40 miles per hour. Jeez. File, save. Okay, so again, 40 miles per hour. We know that the density of the air is 1.204 kilograms per cubic meter. And we're operating at the BETS efficiency of 16/27. We also know that we have 10 kilowatts of power coming out. So the question is, what's the area of the blade? Okay. And I just realized I made one little mistake, but we'll fix that easily. So we started off with the formula for kinetic energy, E equals 1/2 mv squared. We then know that power equals delta E, delta T, or power equals E dot. It's the time rate of change of energy. So we can just basically say that the velocity of the air blowing through is constant, and it's really this mass that's changing. So here comes a chunk of mass 1, chunk of mass 2, and we can look at delta T as this change in time as the masses come through, or we can just call the whole thing m dot that's flowing through the turbine, these masses of air. So that's what that is. Okay, so that's how we get our power. And we know that that's the power in, or the mechanical power. And we also demonstrated that the rate of flow of mass, the bigger the area of the turbine, the more dense the air, and the faster the velocity, the more mass flows through. And we confirm that area is length squared, density is mass per length cubed, velocity is length per time, and that gives us finally mass per time, because we've got length squared times length in the numerator divided by length cubed in the denominator. Those disappear, we're just left with mass per time. Okay, for our mass flow rate. Now, we know the efficiency is the power out divided by the power in. We solve that for power in because what we're looking for is area. So in this equation, we know we're looking for the area. We can get the power in because we have the power out and we have the efficiency. So substitute that in, solve for area. Area equals 2 from this guy right here. Area equals 2 times power in divided by air density divided by velocity cubed. Now we take our efficiency equation, substitute that in, and we have the area equals 2 times the power out divided by the efficiency divided by the density divided by velocity cubed. So now we've got it where we want it. The only thing I left off in my previous calculation was the 2. And so the final answer for the area is 4.9 square meters. If I go up here, I did this, also just ran it in Microsoft Excel. And I use the letter S instead of A for area. That's fine. There's 4.9. So from there we can get the radius. That's just simply the square root of the area divided by pi. And then from there we get the diameter in meters of 2.5 meters. And let's just convert that to feet. Eight foot diameter, 8.2 foot diameter. .28. Let's just do that conversion. Equals 3.28. Goes that number times 3.28. Take off a couple significant digits there. Number. Perfect. Okay. So 8 and a fifth, and that's a pretty big underestimate. It's the total diameter of the turbine is probably closer to double that. It's more like 16 feet, but that just shows you that the Betz limit assumption was relatively inaccurate. And 40 miles per hour. I mean, the turbine is rated for 10 kilowatts. And I don't know what its cutout speed is, but the turbine would be good for 40, 45, maybe even 50 miles per hour. So anyway, just it's at least a good ballpark to show we're at least in the right ballpark for that particular turbine. Okay, and I think if we go back to the exam, 2.5 meters. Oh, I think let me just double check that. Yeah, 2.5 meters. Perfect. Okay. And another thing to keep in mind here, that would only be a 7-centimeter turbine. So, yeah.
I don't know what's going on.
It's okay, yeah. I mean, it's okay. If nothing else, just, I guess on that particular one would be just to guess rather than go with
Well, I had the equations and I wasn't too far off with my way about going about it, but let's see. I don't know where I would run.
Perfect. Okay. So what we've done here, just to catch up, I'm just catching up on all the quizzes from the course. So I went over that kind of tricky one just a second ago on calculating the area of the wind turbine in the Hellgate Canyon with the given parameters. And I know we had an issue with this quiz because you were not given the initial cost. It's there now, so I'd like everybody to finish that up. There were a few people who just hadn't done it yet. But again, we're looking at a $200 solar thermal technology, and you're going to offset an existing electric system. So what we're assuming, you've got 4.4 hours coming in per day, you've got 1,000 watts per square meter of sunlight coming in, and the technology is 2 square meters. And I apologize for not having the subscripts looking any better than that. But electricity costs 10 cents per kilowatt hour. The electric heater you're using is 2,000 watts, and the runtime per day is 4 hours. So I'm just going to take a second and review how to do that. Okay, so we're doing the solar thermal payback. One thing I've written here for energy, I've noted that since this is an electric system, in a electric system, you're heating the house by running electricity through a wire, and we know that P equals current times voltage, and we know that voltage equals current times resistance, so power equals I squared R. And so what I've written here is that energy equals I squared R times hours. And the dollars per day equals the energy consumed per day times the kilowatt hours. So right here, energy equals the power, which I said is 2,000 watts. You're going to run it 4 hours per day, and it's 10 cents per kilowatt hour. So 2,000 watts is 2 kilowatts times 4 hours times 10 cents. You're looking at 80 cents per day. I think I said you're going to run it for 200 days per year, so that's $160 per year that you were going to spend. You're going to spend $160 per year heating your house with electricity. Now, rather than running this system, you're going to do a solar thermal panel instead. And we've made a lot of assumptions here. We've made the assumption that the sun is on when you want it to be on. So there's no storage or what have you, but it's just an exercise in saying again the upper limit of what might be possible here. So if you've got 1,000 watts per square meter coming in, it's a 2 square meter panel. So the power, I just wrote this out as phi. So phi is the power density or the solar flux. So P equals the solar flux times the area. We know that we're 1,000 watts per square meter, 2 square meters, so that's the power of the system. So the system itself it's the same. I mean, you've made a solar heater that's the same power as the electric heater. In general, I would call this undersized because you're going to need some storage. So you might actually double that, triple that, and you might have some hot water storage elsewhere so you can bank that heat so when the sun is not shining, you can draw from it. Okay. So again, energy is power times time. So we've got 2,000 watts. It said the sun is going to shine for 4.4 hours per day. So we're looking at 8,800 watt hours per day, or 8.8 kilowatt hours per day. And that basically means you're making 88 cents of energy per day, per day. 88 cents of thermal energy per day. So the question is, how long is the payback? Okay, so there's a couple different ways to do this. We know the system costs $200 if we assume that we're not having to run the electricity at all. We've basically said that $200 system is going to offset that 80 cents per day, and it's going to take 250 days to pay back. If we just assume that the system is going to pay for whatever of its own energy it's making, that would be 227 days. Obviously, it'd be faster because it's making more than that energy per day. So either one of those is going to be in the ballpark. Let's just take a look at the answer. I'm going to type in 250. See what I get. Answer saved, submit and finish. Finish review. And see my grade. I'll just take a look at somebody else's here.
That'd be like the offset payback.
Yeah. This one you either got it or you did. It looks like everybody nailed this because I've actually given the answer a couple times. Said 227. I think I gave credit for both. So there are a couple different ways to think about this, and I'll give credit for either one.
Yeah.
And the point is that the system does pay for itself relatively quickly.
Yeah, because in a way, the answers are correct. Because 250 days would be the offset cost, so that's like the savings that's how many days it would take to pay back for what you would normally be paying.
Right.
It's still generating that extra energy or that extra heat. I guess that extra energy, because we didn't really specify, did we, that it was heat?
It's heat. Yeah, it's solar thermal. Yeah.
So then the 227, you're still getting that extra money and heat. It's just, and so you're still getting the energy for that. So.
Yeah, and the assumption here is that more heat is good, which could be,
Yeah, true. I guess because we're stretching it for, well, that'd be 227 days of heat to pay it back.
Yeah.
Just feasible.
Yeah. You can do similar calculation on for solar PV, but we can do that in another course. Okay, I'll take a little pause. All right, so the next one we're looking at, I think this gave a lot of people problems too. So you've designed a solar thermal system, and I've noticed that not all of the heat is making it into your house. So after some measurements, you determine at a temperature difference of 20 degrees C that you're losing about 50 watts on your system, and its area is 4 square meters. So what's the heat loss coefficient? So let's just run that. So here's your, we know that 50 watts is leaving is heat. This system is sitting on the side of your house. Sun's hitting it. So it could be losing heat out the sides because it's not insulated. There could be some convection along the back, and it could also be radiating back into space. But however you measure it, you're losing 50 watts. And it's 20 degrees difference between the system and inside. So this delta T is 20 degrees. Now, the equation for heat transfer is Q dot equals U, which is the thermal conductivity, times the area times delta T. Now, so we're going to say that if you made this system bigger, we're just going to assume that you're going to lose more heat through it. So the equation, what we're solving for is U. So U equals Q dot divided by A divided by the temperature difference. So you've got your 50 watts, 4 meters squared, and then that's degrees C. So we end up with 50 divided by 80 equals 0.625, and that's going to be watts per meter squared degrees Celsius. Okay, so that's the answer on that guy. That's what I'm looking for. Make sense? Enough?
Last coefficient system. Yeah.
Yeah.
Before I thought it was.
Another way to think of it is the thermal conductivity. So,
Okay, yeah. Yeah, because that's how much it's.
yeah, another thing worth noting. We can go back up here. I just want to go over these concepts. So we know in a electric circuit, if we've got voltage across a wire or voltage through a wire, the longer the wire is, the more the resistance. So we know that the resistance equals the length times the resistivity times the area. So this rho is the resistivity. Obviously, the longer it is, the fatter the wire is, the better the resistance. So that's what that guy means. So the analogy here for heat loss, we know that the R value is inversely proportional to what's called the thermal conductance, and that's basically what we did there. K is the thermal conductivity, and you can think of that like the resistivity. So thermal conductivity, thermal resistivity. The units of the thermal conductance are watts per square meter per degree Celsius, which is what we just did. If I had given you the wall thickness or the thickness of your technology, I would have been asking for the thermal conductivity. This is basically your heat loss coefficient. It's how quickly heat's flowing away. And then, of course, Q is the symbol for thermal energy that's measured in joules. Q dot is the how quickly thermal energy is flowing, that's measured in watts. The book likes to use delta theta for temperature, and that's fine. That's measured in degrees C or degrees, or just in Kelvin. Another thing worth mentioning is that the R value as well as the U value are called either extrinsic properties or extensive properties, because it matters how much or how little you have. The K value, which is the conductivity, just like electrical resistivity is an intrinsic or an intensive property. It doesn't matter how much you have. And the symbol rho is similar for density. Like, it doesn't, like, for example, if you had a chunk of lead, it wouldn't matter if you had an ounce of lead or a pound of lead, that lead still has the same density. Therefore, it's an intrinsic property. Okay. Yeah. Another thing just showing here is that if I had fiberglass, and if I had one chunk of fiberglass and it had a rating of R10, and I put two of them in series, I can add R values. What you can't add, you cannot add K values. You have to know how much you have in order to add them. So you can add R value, and if we had to do it this way, we could say that, since R equals 1 over U, if we were to add two things, so if we had R total equaled R1 plus R2, we would have to add them like this with the thermal conductivities, or I'm sorry, thermal conductances in the denominator. And you'll see the same thing in electrical circuits. Okay. And this was just an example I did where I actually used the fact that the thermal conductance equals the thermal conductivity divided by the distance or the thickness. And if we go and let's just take a peek at thermal conductivities really quick. There's a few nice little, let's hit the engineering toolbox. So here you can see that the thermal conductivity is in watts per meter Kelvin. Watts per meter Kelvin. And that's why to get to watts per square meter Kelvin, we divide by the thickness. That's where that comes from. And, as expected, let's just look at a few things. Very thermally conductive is agate, this rock. Very unconductive would be argon gas. Yeah, not too surprising. Another thing worth noting, I've seen this mistake made before. I was in a hotel with a geologist, and we were he was touching some solid rock and some fake stone, and there we are in a hotel lobby, and of course his body temperature is 98.6, and the room temperature is more like 70. And he touched the two and he goes, "Oh, look, you can tell that this is fake rock because the real rock is colder." Well, all of the materials in the room are the same temperature. I mean, there's the air is 70 degrees, the walls are 70 degrees. But what's different, the reason the natural rock feels colder is because the thermal conductivity is greater. It's pulling heat away from your hand faster than the other rock. It would be like it's just as simple as that. So the temperatures aren't different. It's this thermal conductivities, and it's the same way that if you walked outside on a cold morning and it was freezing, the air was freezing, say the water was very close to freezing, you would much rather have your hand in the air than in the water because the thermal conductivity of the water is much greater. It's pulling that heat away from you. So you're actually sensing the motion of heat flowing away, not just the actual temperature. Okay, let's take a little break there.